Hello, we are the Anubis team. There are a lot of things around us that may seem unpredictable. We tend to think so when we don't have a clear sense of what they depend on, like the weather, or a simple system like a pendulum with moving support. This is an example of chaotic systems. Speaking of which, one of the most famous examples is the double pendulum problem, and that's the topic of our project. It is considered chaotic because of its sensitivity to initial conditions and other uncontrollable factors like air resistance and friction of moving parts. To make the problem easier and decrease the number of variables, we restricted the motion to be in 2 dimensions only. There are multiple methods to model this system, like Newton's equations, or the one we will use, Lagrange's equations, as it has a simpler approach. We started our solution with the principle of least action. It states that the path taken by a free-moving body to move between 2 points is the path where action is minimum, meaning the difference between potential and kinetic energy is the least it can be. Using Euler Lagrange equation, which is a partial differential equation, we were able to find a solution using the 2 pendulum masses, the angles they make with the vertical axis, and the length of the 2 strings. After getting these 2 equations, we use the MATLAB code, where we can specify the initial conditions to solve the equations numerically, model the system, and predict how it behaves when certain variables change. Where we can specify the initial conditions to solve the equations numerically, model the system, and predict how it behaves when certain variables change. We can solve the equations at each moment of time to get a real-time simulation. Using all the numerical results obtained in real-time simulation, we can draw a no-time graph.